he has kindly agreed to speak about recent work he has done on the cube, which is, as I said, a very cool polytope, especially regarding triangulation.
Thanks very much. I'd like to thank the organizers for the opportunity to tell you a little bit about cubes. The D cube, the D-dimensional cube, is a fascinating polytope. And when I first started thinking about cubes, I thought that, they're rather simple objects, and maybe there isn't that much that can be said that's interesting. And I was very surprised to learn that, in fact, there's a lot about cubes that isn't known. And what I'd like to tell you a little bit about today is first I'd like to tell you a little bit about cubes and give you some general background to the study of minimal triangulations of cubes. And then I want to tell you a little bit about how I've been thinking about minimal triangulations in terms of minimal simplicial covers. And I'll tell you what those are in a little bit. And then I'll give you a survey of some of the methods that I've been interested in developing lower bounds for minimal triangulations and minimal simplicial covers. I'd like to say that the material in the last section here is joint work with an undergraduate student at Harvey Mudd College, Adam Bliss, who pursued much of this research during the summer and then his senior thesis last year. Okay, so I gave you a warm-up sheet. Since I'm giving this talk in lieu of a problem session, I thought I'd get you started by thinking a little bit about cubes. So first, let me tell you a standard triangulation of the cube, and I don't know if you saw this earlier in the workshop, but it's a very simple way to triangulate a cube. Turns out there's a standard triangulation of a cube of size d factorial for a d-dimensional cube. And an easy way to think about it, if you want to think in terms of the vertices of the simplices, is to do the following. Take a permutation, and to every permutation, let's look at the 3 cube and look at the permutation 3, 1, 2. I will associate the following simplex. The simplex will always have 0, 0, 0 in it and 1, 1, 1 in it. And the permutation is going to tell me the order in which I increment the vertices to get the other vertices in the simplex. So in this case, each of these are the vertices in the simplex, and this is the one associated with 3, 1, 2. You can see from this that there are, in fact, d factorial of them. Maybe it's not so obvious that they're all disjoint. And so another way to think about this triangulation is if you have a permutation in the symmetric group, you can associate to it the set of all points in the cube where that particular permutation of variables it satisfies the following inequality, sigma d. So the set of all such points forms one simplex in the d cube, and here it's clear that any set of any points in the d cube is going to satisfy some relation like that, and only one such relation unless it's exactly on the boundary of one of them. And those are the common faces. Okay, so there's a standard triangulation of the d cube, and this, of course, yields for the 2-dimensional cube. It happens to be the optimal triangulation, and that's the last case in which it's the case. And I didn't realize this, but I guess you already had a homework where you pursued the minimal triangulation of the 3 cube. That's one of the warm-up problems. Let me see if you remember some other things from earlier in the week. What can you say about the volume of simplices in the cube? So if I'm going to triangulate a cube, it's going to use simplices from the vertices of the cube. What can you say about the volume of such simplices? Let's see. How do you calculate the volume of a simplex? Form a matrix with rows or columns as the entries, and augment a row or column of 1s, and take the determinant, and that determinant's always going to be what if all the entries are integers? It'll be an integer, and then you normalize by what? D factorial. Thank you very much. Yeah, so just to make things simple and nice, I'm going to speak of the volume of the simplex. I'm not going to, when I do that, I'm not going to divide by that d factorial. Okay, so that way in the 3 cube, the possible volumes are 1 through 6, and in fact, you can't get a a volume 6 simplex, right? You could only get volumes 1, 2, and any others? I think maybe worth thinking about. It's probably something you may already be thinking about. I'm going to call that volume, the normalized volume, I'm going to call that the class of a simplex. Okay. Okay, so there's one question. So why is the standard d factorial triangulation of the cube maximal? Let's see. What is the class of the cube? It can have at most volume what? 1 or class 6, right? And so the sum of the classes better add up to 6. And what do you know about the classes of each simplex? They're an integer, so if it's not degenerate, then it's going to be 1, right? So you can see here that the d factorial standard triangulation in general is going to be maximal. Okay, so apparently you've actually thought about the minimal triangulation of the 3 cube. So how do you get smaller triangulations? Do I want to use class 1 simplices? Well, I'd like to use ones that have bigger volume, right? Okay, so you perhaps showed that you know what the minimal triangulation of the 3 cube is. It looks something like this. Basically, does it use? Is there any fat simplex in this triangulation? The one in the middle. Okay, this one happens to be class what? 2, because the other ones, the corner cutters, are obviously volume 1, and there are 4 of them. Okay? Okay, so these are sort of the beginnings of the ideas that you encounter when you start studying cubes. So why does this have to be minimal? Volume can't be bigger than 2, but if the volume were 2 for all of them, I could get something of size 3 perhaps. How come I can't use all volume 3 simplices, volume 2 simplices? What you just said is a very good idea, and in fact, you'll see one of the lower bounds uses this idea that the maximal volume is size 2, right? So 6 divided by 2 is 3. I need at least 3 simplices. But why do I need at least 5? Ah, yes. Okay, look at the faces. What do you notice about the face of a cube? It is again a cube. And in dimension 2, what do you know about any triangulation of the 2 cube? You must use 2 simplices, right? And these in their own dimension are what class? 1. Okay. How does the class of a simplex relate to the class of its facet? If its facet is exterior. It's sitting on the bottom of this cube. Let's see. Volume equals some normalization to base times height. But when I forget the normalization, it's just base times height. That's the nice thing about classes. So what do you know about the class of any simplex that has an exterior face? It must be what? It must be volume 1, because this base is volume 1, and this height is what? 1. Okay, so if it's going to cover the faces at all, it better have volume 1 simplices. How many volume 1 simplices must it have? Well, let's see. The volume 1 simplices, let's see, that cover this face might actually come from the same simplex, right? Can you name me 4 simplices that whose simplices can't be the same? Yeah, opposing faces. Thanks. That's great. So if you look at the opposing faces, Of course, you have to use a little linear algebra to verify this in higher dimensions, but in dimension 3, you probably can see this. It's impossible for a simplex to have two faces on opposite sides of the cube unless one of the faces is dimension 0, a vertex. Okay, you would need to verify that in higher dimensions, but you can see that here. So in fact, you know that this face is covered, this face is covered. They must use volume 1 simplices, right? That's 4 of them, class 1. And then you need 2 more for the other, so 5 must be minimal, right? Okay, well, I just sketched for you some of the basic ideas and what I want to tell you about later. So, okay, so we're trying to answer this question: what is the size and minimal triangulation of the D cube? And there's a lot of work that's been done on various aspects of this problem. I want to focus on lower bounds, but I will tell you a little bit about upper bounds. In fact, let me tell you a little bit about upper bounds now. So how would you try to, actually, I don't have this sketched on the slide, but I do have this sketched in the handout. Let me tell you about specific constructions for D cubes that are optimal. So this is the optimal minimal triangulation of the 3 cube. How would you go about constructing a minimal triangulation of the 4 cube? Any ideas? Just throw out some ideas. It's okay to venture a guess.
Same kind of thing, maybe? Chop off the corners?
Yeah, maybe chopping off the corners. In fact, those were the beginning papers on the subject actually pursued this. For instance, Mara, in 1976, produced the following triangulation of the 4 cube. So what is the 4 cube? Well, it's an object, all of whose facets look like what? 3 cubes. Okay, so let me just tell you then that the great, 4 cubes all over the place. Look at that. Okay, so all of whose facets are 3 cubes, and in this representation, the Schlegel representation, we're just looking at the boundary of this 4 cube. That is, this is a facet, this is a facet. Each of these are facets, and there's one big facet out here. Okay, and there's some volume spanned in the middle. Each of these facets, how many of them are there? 8 of them. Each of these facets are covered by facets of simplices in the 4 cube. Okay, and that cover of each of those 3 cubes looks like this. Okay, so this was Mara suggested a triangulation of size 16. And you can see why it's size 16 from the observations I just made. Namely, what do you know about this particular triangulation? Well, let's see. How many corners have I cut off? I'm cutting off. Turns out that what you get is you're cutting off alternate corners. How many vertices are there in this cube? 16, and you're cutting off half of them. Okay, so that's how many simplices? 8 of class 1. Okay. Now we need the class to be what? Total up to 4 factorial, which is 24. Okay. And so what Mara does is he triangulates the rest with class 2 simplices, 8 of them. Okay. And in fact, you can see what the bases of those simplices are. They're just the big simplex in the middle here. The basis of those simplices are the 3 simplices that are these. And for reasons that will become apparent later, I'm going to call this the Hadamard simplex. It's the big fat simplex in the middle of the 3 cube. If I need to, I'm going to call these corners. Let's just explore your intuition a little bit. What other possible isomorphism classes of simplices could there be in the 4 cube? A 3 cube. Well, let's see. You can draw a few pictures. Well, they're the ones that make up the standard triangulation. Okay, and those basically walk from here to here, advancing along certain coordinates. Okay, so I'm going to call those permuters. And there's one more. Anybody see one? with a little thought, you'll realize that there's another isomorphism class. Looks something like this. That's the base of it. And then instead of cutting off the corner where its top vertex would be here, it actually leans over. So I'm going to call this a leaner. Okay, and so you have basically 4 kinds of simplices in the 3 cube. And as a little bit of homework, which you can think about, it's fun to think about some of the relations between these. It turns out if you take 3 leaners, you can, see if you think about this. If you take 3, is it 3 leaners? Yeah, if you take 3 leaners, you can get a corner plus a Hadamard. That is by putting them together and cutting them a different way. What's another relation you see? You might, for instance, yeah, if you take 2 permuters, you can in fact get a corner plus something else. Anybody see what that is? Corner plus a leaner. You might verify that just to have some fun. Now, suppose I wanted to look at simplices in the 4 cube. How would I begin doing that? How would I try to understand the isomorphism classes of simplices in the 4 cube? Let's see. Some simplex in the 4 cube. Well, what's that?
Like cone each of these to vertices in the opposite cube, the other end of the 4 cube. So consider simplices whose bases are a permuter or a leaner or a
Okay. Okay, great. Yeah, so in fact, what you're suggesting is I could look at simplices, first of all, ones which have exterior faces. So their base is some simplex here, and then above it, this is the upper half of the 4 cube. It's the 3 cube fasten on top. This is the 3 cube fasten on bottom. And you could look at ones, first of all, whose base is one of those 4 kinds, right? And then what do you know? What do you do with the other one? Well, it could be, one of a number of different possibilities, right? So there's a lot of possibilities here. Some of them are going to be isomorphic. Now, how many people think that this is quickly becoming hard to do? Yeah, OK. So this is something that I guess in some of my work I want to avoid trying to enumerate isomorphism classes. OK, and you'll see that some of the previous work has tried to enumerate these with a lot of success. So OK, so now that we've had a little primer on cubes, let me tell you a definition that will be important: a simplicial cover of a polytope. So I want to consider generalizations of triangulations where you allow overlap. Okay? So here, a cover of the pentagon might be this triangle with all its 5 rotations, 4 rotations, 4 other rotations. Okay? And we allow overlap, but we only allow vertices from the vertices of the polytope. Okay? And so a question you might ask is, what's a minimal triangulation or a minimal cover? I'm going to call C of P the size of the minimal cover. Now, if you have a minimal, if you know C of P, do you know anything about the size of minimal triangulation? Well, let's see. There's actually, have to be careful about what we mean when we say triangulation. But you can see that since a triangulation is a special kind of cover, then the size of minimal triangulation must be what? Smaller than, bigger than the size of the minimal? Must be bigger than or equal to the size of the minimal cover, right? Size of minimal cover must be smaller than or equal to the size of minimal triangulation, right? Okay, let's do a little example here. So here's a non-convex example. I'm only going to consider cubes, convex polytopes. But non-convex example, you might, for instance, have a hexagon, not a hexagon, a 6-sided star that's covered by 2 simplices. But if you try to triangulate, it needs at least 10 simplices. Okay, so the minimal cover might be smaller than the minimal triangulation. And it's an interesting question to ask when that occurs and if there are any good examples. Okay, so why care about minimal triangulations? Well, you already know some answers to that question. So one motivation for the study of this is efficiency of certain simplicial algorithms. So it turns out that in the 60s and 70s, a constructive version of the Brouwer fixed point theorem was found, and people love using fixed point theorems to prove various things. And so if you have a constructive version, it certainly makes it nice to be able to find fixed points constructively. And the way these methods work is they take the domain that you're interested in, break it up into lots of small simplices, and then hop from simplex to simplex through the triangulation. Now, what's the running time of the algorithm? Well, it's going to be dependent on what kind of triangulation you pick. And certainly you'd want triangulations with what? Small numbers of simplices. Okay. Now, one way to, if you have a big domain, you know, you could triangulate any which way, but how are you going to tell a computer to do that? Well, an easy way to do that is to triangulate the domain by lots of cubes first, and then triangulate the cubes, right? Okay, so this is one motivation. Jesus talked about other motivations. And of course, I guess my interest in the subject has been using such simplicial algorithms to solve certain fair division problems, which is another talk. Okay, why else? Well, knowing something about minimal triangulations is intrinsically interesting. Okay, and that's why a lot of us do mathematics. So why care about minimal covers? Well, one reason is that they arise as images of certain simplicial Brouwer maps, whatever that means. I'll give you some feeling for that in a minute. And another is they give lower bounds for any kind of triangulation. And something I want to stress here is that in the literature, when you talk about sizes of minimal triangulations, there are lots and lots of bounds out there, and they refer to different kinds of minimal sizes. So, for instance, you could talk about minimal triangulations where you only allow vertices of the simplices to come from vertices of the cube. Okay? Now, you might wonder if I put in extra vertices, if I could get a smaller triangulation, right? And Jesus referred to examples in other domains where that can be a possibility. Does that happen for cubes? That's an unknown question. The notation I'm following is that of Smith, who used T sub v to indicate minimal size of triangulations where you allow vertices to only come from vertices of the cube. Okay? But there's also the version where you don't care. Okay? The F here refers to triangulations that are just face-to-face, and I think those are the only kinds you've been considering in this workshop. But you might, for instance, allow dissections, as they're sometimes called, to be ones where simplices don't meet just face-to-face. So, for instance, take the triangulation of the octahedron by 2 simplices here and here, and twist. That would be an example of a non-face-to-face triangulation. For the most part, you've only been thinking about these kinds of triangulations, I think, or maybe these. Okay, and a lot of the bounds in the literature are for these quantities. Okay, so you have to be a little careful when you look in the literature. In terms of the notes that are in your handout, I've given you some of the constructions in the past work that's been done on triangulations of cubes. So we know that if D is 3 and 4, the minimal triangulation in various incarnations of this, well, 3 it's 5, and 4 it's 16, but this result for 16 is for ones without extra vertices. And actually there is one of 15 where you allow anything. Okay. For 5, it happens to be 67, and I can give you some hint of how that goes, if you take the 5 cube and you cut off the corners, let's see, the classes have to add up to 120. Quick computation. I'm cutting off 16 corners. That leaves 104 things left, volumes left. And if you do those all with volume 2 simplices, you'll get 68. So with a small tweaking of the 68, you can get 67. It's a non-symmetrical triangulation. And this 67 is just for TV. The 6 cube is 308 if you want TVF. And it's 270. It's at least 270 if you want TV, but as far as I know, that's not known. And for the 7 cube, the numbers look something like this. And these are actual constructions. And this is a bound. And if you want something asymptotic in higher dimensions, there isn't too much known. But if you want non-exact answers, you need to talk about upper and lower bounds. So let me say a little bit about that. So for upper bounds, how do you get upper bounds for the minimal size of a triangulation? What do you do? Well, you could construct a good triangulation, right? Try to construct one that's small. That's certainly an upper bound for the minimal size, right? In this connection, there was work of Heyman in '91, and actually a recent paper by Francisco Santos and David Orden, who are here, where they use an iterated construction. That is, if you know something about how to triangulate one polytope cross another polytope, you can iterate that to get triangulations of bigger and bigger cubes. And in fact, David and Francisco's work is the best known upper bound now. And correct me if this number's not accurate, but I think it's something like this. Okay. And you can see that this is, let's see, what's the biggest triangulation? It's d factorial. And this puts a constant to the d in front of that. Okay. Heyman had a constant of 0.84 to the d factorial. And I guess what I've been interested in is lower bounds. So let me give you some idea of how you might go about thinking about lower bounds. Okay, so the first method that I want to talk about actually also relates to something Jesus mentioned earlier. And this is what I will call a pebble set. So a pebble set for a polytope is a set of points, which I'll think of as pebbles, such that every simplex contains at most one pebble. So for instance, for this pentagon, you can check that any simplex in the pentagon will contain at most one of these red stars. Okay? So a little challenge to you is to place as many pebbles as you can in this polytope. This is the hexagon. Place as many pebbles in chambers so that each simplex contains at most one pebble. Take a minute to do that. You could start just by randomly placing them, right? But how could you do that? And why does this relate to minimal triangulations? Let's see. Oh, if I place one right here, then can I place another pebble here? No, because this simplex would then contain two pebbles, right? So I have to avoid any simplex that contains this pebble. What about this one? Now I'm restricted here. Can I place one here? 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 Yeah, I could if I wanted. And in fact, I can place another one. And you'll see that this is, in fact, 4 is as many as you can do. Maximum number of pebbles is 4. OK, now why does this relate to minimal triangulations? let's see, if you have a minimal triangulation of if you have a triangulation of this hexagon, and every triangle in the triangulation contains at most one pebble, then what does the number of pebbles tell you? Lower bound for the minimal number of triangles. In fact, it gives you a lower bound for the minimal cover as well, because we didn't use anything about overlaps. Okay, so this is a nice way to get lower bounds, and I just explained why. And what I showed in a paper with Jesus and another Harvey Mudd undergraduate is that for arbitrary polytope, you can get an arbitrary bound in terms of the size, of the number of vertices, and the dimension. And what this means is something that is not so exciting for cubes, but for general polytopes, the covering number is at least n minus d. Of course, this depends on some construction, which I don't have time to tell you about. But that particular construction is not so good in terms of what this lower bound says. Okay, you can see the numbers here. Well, after dimension 3, we're in trouble. Okay, and in fact, placing pebbles, the construction that Adam worked on here is could only place 12 pebbles in a 4-cube, and it's an open question whether you can place more pebbles. And in fact, if you think about this, there's nothing special that said I had to use whole pebbles. I could also use fractional pebbles, as long as the sum of the pebbles inside each simplex doesn't add up to more than 1. This is like fractional graph theory, for those of you who know about fractional graph theory. And fractional pebbles, in fact, you might be able to do better. And in fact, you should be able to get 16 with fractional pebbles by a certain duality, linear programming duality. But OK, so this is a method for getting lower bounds. But the general method for polytopes doesn't do so well for cubes because we haven't used any of the geometry of the cube yet. So here's a challenge. It's a good question for some of you who want to think about it. Is there a construction specific to cubes that might do better? Let me give you an example where, in fact, it does. So some of you, all of you now know about the cross polytope. But you can think about octahedra if it helps. Let's just, for d equals 3, this is the octahedron. Let's see. Well, the octahedron has how many vertices? It has 6 vertices, right? So the n minus d bound here is, let's see, 6 minus 3 is 3. But I claim you can actually place 4 pebbles if you're clever in the chambers of the octahedron. What are the chambers of the octahedron? Let's see, intersect all possible simplices you can get. What are the chambers here? I claim they all the dividing planes pass through, well, actually, they're just cut out by the coordinate planes. Okay, how many chambers are there? 8 of them. Okay, and I claim you can place 4 if you're clever. Anybody see how? Yeah, how about placing ones in, let's see, let's put one here in alternating chambers. That is, these 2 are here and these 2 are here. Okay, and if you'd like, think about the dual of this. It's the corners of the Hadamard simplex in the dual. Okay. If you place these pebbles, this in general actually gives you 2 to the d minus 1 pebbles. And this is, in fact, the right number for the minimal triangulation. This is the minimal triangulation. So if you're clever about this construction, you might be able to do better. Can you use this technique for cubes? That's a question. Just do it for do it for a specific dimension, d equals 3, 4, or 5. OK, well, there's one technique. I am not going to. Well, I'll tell you just briefly. There is a consequence of this there's just one idea in this consequence that's useful for us. There's something called the polytopal Sperner lemma. For those of you who might have heard of Sperner's lemma, this is a generalization. If you take a triangulation, you can label the vertices, and that's an interesting combinatorial object. And if you label it in a particular way, it's going to be called a Sperner labeling. So the particular way here is, let's label all the main vertices of the polytope by different labels. And then on each face of the polytope, you only allow labels from the main vertices that span that face. And what we're looking for here are what are called full cells, that is, simplices in the triangulation with all different labels. And in this paper with Jesus and Elisha Peterson, we were able to show that this pebbling set argument actually gives a lower bound for the number of these full cells. Those of you who don't know anything about Sperner's lemma, it turns out that it's equivalent to the Brouwer fixed point theorem in topology. And so this is kind of interesting from that viewpoint, because in the proof, you use a certain idea that will actually be useful for us in terms of triangulation. So let me tell you about that. So the idea of the proof is to look at simplicial maps. So let me tell you what that is. If I had some triangulation of some polytope, okay, I'm not going to continue this. Oh, I can't stop. Okay. And I label the vertices in some fashion. You can actually construct a map of the polytope to itself in the following way. It's a natural map associated to the polytope, a self-map of the polytope, that basically maps every vertex to its corresponding main vertex. So where is this simplex going to go? The 2, 3, 4 simplex. Well, 2 will get mapped to 2, 3 will get mapped to 3, and 4 will get mapped to 4. And then you extend linearly. Okay, so this is a certain piecewise linear map. Okay. And if you're looking for full cells, then they just correspond to simplices that don't degenerate under this map. Okay, so if you're looking for, if you know there are a certain number of pebbles here, you know there are a certain number of full cells here. Now, one interesting observation about this map, if this labeling is a Sperner labeling, is that if labeling is a Sperner labeling, then this particular map will cover the entire polytope. Okay, and those of you who know anything about degree theory will see this map is degree 1, if you had topology background. Okay, so if it covers this polytope, then you get this particular consequence. But you also, if you think about it, see why lower bounds for covers actually give lower bounds for any kind of triangulation, even ones with extra vertices. And the quick argument is the following. If I have a triangulation with extra vertices, like say here and here, well, that's some triangulation. I could give the interior vertices any label I want. This will be a Sperner labeling. And under this particular piecewise linear map, these colored simplices go to these colored simplices. But this observation that this self-map is going to be of degree 1 means that the entire image here gets covered. So to every triangulation, including ones with extra vertices, what do I know about the image simplices? They form what? A cover. Okay, so if I have a lower bound for covers, I will have a lower bound for triangulations, because these simplices, some of them may degenerate, but every one here comes from one here. Okay, so that's the main observation that helps us. And that's the end of the discussion of the first lower bound technique, and maybe some of you can do something with that. A second lower bound technique is a volume calculation that, in fact, this gentleman here alluded to. You could do the following. We already know this. simplex has what kinds of volumes, multiples of 1 over d factorial. So here's a silly bound. That turns out to be not so silly once you, no idea is too silly. Okay, but it's going to seem silly at first. A lower bound for the covering number is, well, let's see, you could take the volume of the polytope and divide by the volume of the largest possible simplex in it. Okay? That should make sense to us because then, you know, the average volume is going to be smaller than the largest volume. Okay, so, well, okay, for cubes, the problem with this is that exact values of the largest possible simplex are not known. This is something that's referred to as a Hadamard determinant problem. There's a lot of literature on that. And that being the largest simplex in dimension 3 is why we call that the Hadamard simplex. So for the 3 cube, it doesn't give such good bounds. And for the 4 cube, it doesn't give such good bounds. But was there anything in this particular observation that required us to use Euclidean volumes? No. So in fact, Smith got a lot of mileage out of this by using a hyperbolic volume to do the computation. And the way of thinking about this is if you place this cube in the hyperbolic in hyperbolic space, then what does hyperbolic space tend to do? Well, it makes the volume towards the center smaller, and volumes towards the boundaries bigger, right? And so this tends to average out the sizes of all the simplices. Okay, and in fact, these bounds that Smith got are actually now the best known lower bounds, not for TV or any, but for T. So this is due to Smith, for instance. This is for T. And there are better lower bounds. I have a slide for the other things as well that's coming up. Okay, so there's a nice idea. In fact, that dates back to, that idea comes from Slater, Targin, Thurston, which Jesus also referred to in his talk. Okay, here's the last technique I want to talk a little bit about, and that is what I like to call looking at the exterior face real estate. Okay, that is, people are always concerned about how much property they have. We just want to keep an accurate count of all the property that we have, not just the interior property, but the boundary property. Okay, this will hopefully give us some constraints that we can work with, and you've already noticed the first two things. And the goal here is to try to do better than Smith. The goal is to try to get bounds, lower bounds for T, and not just TV and TVF. Okay. I should say that these observations and these ideas follow work of Anderson and Hughes, who were getting bounds for TV and TVF. Okay, so what I want to do, if I'm not going to keep track of all the configuration classes, which is what people have done in the past, then I have to be more careful about how to count exterior faces. So I'm going to define a function that'll count the number of D prime faces of class C prime that a D simplex of class C can have. Okay, and this I promise you is the first time I've ever worked with a 4-variable function. Okay, and what good is it if you can't count it? Well, that's a good question. Okay, let me show you what I'm going to use it for, and then you'll see why it might be interesting to count this thing. So here's the idea. We know that cubed faces are covered by the exterior faces of simplices, right? So if I just look at the class of a simplex and let x sub c be the number of simplices that have that class, then what is the size of the cover or the triangulation going to be? It'll be the sum of the xc's, right, over all possible classes. And what do I want to do with this quantity, sum over xc's? I want to minimize that if I can, right? Oh, okay. Well, then what are the constraints? So this is beginning to look like a linear programming problem. That is, it is a minimization problem that has some linear constraints. And the linear constraints actually just count the exterior face real estate in dimension D, D prime. So let's see. What am I doing? This is the number, let's see. This is the number of simplices of a certain volume, okay? This is how many exterior faces it can have of a certain type. This is the volume of the exterior face. This is the normalization to get the actual volume. This is the sum over all the possible classes of the faces and the simplices. And this is the volume of all the faces in dimension D prime. Okay. Okay, so let's step back and analyze this. This looks gory, but what do we have? We have a linear programming problem with how many variables? Well, not that many, because it turns out that the maximum volume in dimension D is pretty small. And when you compare a linear program with 9 or 32 variables to one with thousands of variables, it turns out to be a lot quicker and easier to solve. And let me then just give you an idea of what happens with this, or how you actually count the function f. So here the function f is the quantity that is going to be the linchpin in this. And it comes back to a lot of stuff that you've thought about in the workshop. Now, for some reason, I always switch between using rows or columns for vertices, but bear with me. Here I've made vertices of the simplex a column in a matrix. And what I want you to notice is that if I want to pick a particular face of a cube, then it amounts to picking k plus 1 columns. And if I want to pick a face, if I want to pick a face of a simplex, it amounts to picking the columns, because those are just the vertices that are mentioned. If I want to pick a face of the cube, then it amounts to identifying a certain number of rows, k rows. And the basic idea is to use some linear algebra to understand what's happening then if I want to figure out what the function f is doing. I know what the volume is. It's a determinant. And this idea that we noticed is that shears preserve volume. So if I have a simplex with a certain base and I shear it, it doesn't change the volume. Okay? And in fact, this base facet then will remain the same. And this other exterior face, tau, will get pushed over in some fashion. It'll still be some exterior face of some simplex on the cube. That's the important thing. And in terms of what's happening with the matrix, you're just zeroing out a whole corner of the matrix. Okay, well then, what is that? What good is that? Well, if you don't mind then, this shearing operation, I'm going to call this sigma the footprint of this simplex, and I'm going to call the image of this exterior face tau, its image in the orthogonal complement, I'm going to call that the shadow. So every exterior face has a footprint and a shadow. And now if I want to count the exterior faces, I'll just note that exterior faces of exterior faces are exterior. And then you can get a nice recursion relation. And I won't go into the details here except to say that the recursion is just saying that I'm looking, if I want to count the number of exterior faces a simplex can have, I'll look at all the possible ways it can have footprints and shadows. Okay. And once you get an upper bound for this, you're in good shape. And so the nice thing about this is that with just a little bit of computational effort, you can get bounds that beat Smith. These are good lower bounds for covers and any kind of triangulations, including extra vertices. They beat Smith in dimensions up through 12, and it's not clear whether they will continue to beat in general. And in fact, I'm now pessimistic about that.
Why
Yes.
are those numbers not the same as
Oh, they're not the same? Did I copy the wrong numbers? Oh my gosh. Ah, yes, yes. The reason they're not the same is they're almost the same. Is that if you solve the linear program, you get those numbers. If you solve the integer program, you get slightly better numbers. And they're only slightly better, I think, in dimension 7 and dimensions 10, and maybe higher. Yeah. So it's just the difference between integer and linear programming. And just to compare, the best known lower bounds for vertex-only triangulations are from Hughes and Anderson. And that's, you can see that they're close. And in fact, one might be able to improve these bounds if you wanted to take into account configuration classes, okay, which I haven't done. And somebody who's willing to be patient and actually go through and count the configuration classes, actually Hughes and Anderson have done it, might be able to improve these bounds and make them close. But you can see they compare pretty well to Hughes and Anderson. Okay, so in fact, just for comparison now, here are some upper bounds these are upper bounds for the minimal triangulation, and these are the actual constructions. Equality comes from, let me put these closer. Equality comes from an actual construction. We know that's the exact number, and then these are upper bounds. And I don't remember if I actually computed these from the Orden-Santos bound, or I believe I did, but in any case, the asymptotic bound here is the best known on the upper bound side. Okay, just to conclude then, I'll give you some further questions that you might want to think about, and these are also in your handout. One thing that we're interested in doing is solving the LP analytically to get an asymptotic lower bound. And we could just, in fact, try to find a feasible solution to get a lower bound for a feasible solution to the dual, get a lower bound for this. Something you might want to think about is finding a cover of the phi cube that's smaller than size 67, or showing that the smallest cover has to be size 67. I mean, it's possible that if you allow overlap, you might have more symmetry than the minimal triangulation. The other thing that this also begs the question is does adding extra vertices help? We don't know if that's true or not for the 5 cube. One thing that our results imply for the 4 cube, notice that here our lower bound gives 16 for the 4 cube. And so what this means then is that we can actually improve this to 16. That is, we know that adding extra vertices in the 4 cube does not help. Okay. So now dimension 5 is the first case where we don't actually know whether adding extra vertices helps or not. So that's something that perhaps some of you may want to think about. Another question is to find a good pebble set construction for any class of polytopes, not just cubes. And this is the other question that I asked. When does adding interior vertices help? Thank you very much. Oh, that's a good question. I believe that was an actual construction, but I don't know the details. Do you know?
Yeah, they essentially they enumerate all the isomorphism class of simplices in dimension 7, and they set up a linear program, which essentially amounts to also count all the possible dimension 6 simplices in the dimension 7 cube, and then for each of them you have this, essentially this, and then finding the construction. So finding the construction that matches the meaning of that program.
It's a tour de force. I mean, they really do just push through and crank everything out.
One question: is any generalization of Sperner's lemma for more than 2 dimensions?
the polytopic spurner that we talked about is a d-dimensional. Yeah. So in fact,
The spinner lemma is true for 2 dimensions also.
yes, that's correct. And our polytopic spurner version is a d-dimensional version. Yeah. Other questions? Well, thanks again.